Born from swirling nebula dust and blazing impacts, our world formed as a molten sphere of rock. Over tens of millions of years, relentless collisions and volcanic outgassing built Earth's early atmosphere of steam, carbon dioxide, and nitrogen. Lightning arced across the darkened skies, sparking prebiotic reactions on mineral-rich shores. As the subsiding heat allowed the surface to cool, torrents of rain fell from the thick, steamy sky, carving basins that filled with roiling turquoise seas. In these restless waters, bathed in diffuse sunlight and nourished by chemical-rich vents, the first stirrings of life awaited their humble beginning.
Raindrops pummel the scorched surface in endless rhythm, each impact sending up hissing plumes of steam that dance across the blackened rock. Mist swirls in ghostly eddies, weaving between jagged ridges and funneling into shallow depressions carved by ancient torrents. Inch by inch, water gathers, first in trickling rivulets, then in widening sheets that merge into nascent pools. These growing basins, framed by cooled lava and ash, shimmer under a veiled sky, their surfaces rippling with every fresh cascade. In this looping ballet of drop, steam, and flow, the planet's first seas steadily take form.
Sulfur-laden air, igniting chemical reactions in a roiling haze. Far below, hydrothermal vents yawn open on the ocean floor, expelling superheated, mineral-rich fluids into the icy depths. Here, amidst thunderous crashes above and hiss of scalding plumes below, simple gases like methane, ammonia, and carbon dioxide collide with dissolved metals and salts. In this churning cauldron, organic molecules assemble, precursors to amino acids, nucleotides, and lipids. Day after day, the tempest and the vents work in tandem, stirring a primordial broth so rich in life's raw ingredients that within its swirling depths, the seeds of biology are quietly sown.
In the warm, restless waters of Earth's newborn oceans, simple molecules, formed through lightning, volcanic gases, and deep-sea vents, begin to interact. Fatty acids align into fragile membranes, enclosing clusters of organic compounds within. These primitive bubbles drift through the chemical soup, absorbing nutrients, replicating patterns, and slowly becoming more complex. Though lifeless still, they show remarkable behavior, gathering, growing, even dividing. These early protocells, delicate and unstable, mark the turning point, the transition from chaotic chemistry to organized, self-contained systems. In their fragile forms lies the blueprint of biology, the earliest hint of life's extraordinary potential.
In the depths of Earth's primordial seas, fragile protocells, tiny bubbles of fat and molecules, begin to stir. Though not truly alive, they grow by absorbing nutrients from their surroundings, their membranes stretching and shifting with each new addition. Some divide, splitting into smaller forms that carry traces of their original structure. Others collapse, while a few persist, adapting, changing, becoming more efficient at survival. These precursors to life begin a slow dance of evolution, driven by chance and chemistry. In their simple, silent struggle lies the foundation for all living things yet to come. In shallow coastal shallows, thread-like microbes weave sticky biofilms over sediment grains, their glowing filaments trapping sand and silt. As each layer accumulates, Minerals precipitate around this living mesh, binding grains into solid, rippling mounds of stromatolites. Over centuries, these microbial mats build towering biorocks, transforming loose deposits into living stone. In their silent, steady growth, these tiny architects record Earth's earliest biosignatures in layered, fossilized tapestries.
In Earth's ancient seas, microscopic cells harness sunlight to split water molecules, exhaling oxygen as a glimmering byproduct. These tiny pioneers breathe out currents of O2, slowly transforming the sea's chemistry. Dissolved iron oxidizes and settles as rust-hued layers, while free oxygen accumulates, enabling new metabolic pathways. Over eons, this silent respiration refines the marine environment, clearing waters, spawning ozone shields, and unlocking ecological diversity. The unassuming exhalations of these cells sow the seeds of Earth's oxygenated atmosphere and set the stage for all future complex life.
In the iron-rich oceans of early Earth, the oxygen exhaled by photosynthetic microbes begins to react with ferrous iron dissolved in seawater. Tiny rust-colored particles precipitate out, drifting down to settle in rhythmic layers on the seafloor. Over millions of years, these alternating bands of iron oxide and silica compact into towering banded iron formations, ancient tapestries of rust and stone. Each stripe marks a moment when oxygen levels rose just enough to bind iron and fall out of solution, then receded again. In these striped monuments, buried deep within cratons, we read Earth's early breath and the legacy of those first oxygen makers etched in solid rock.
As rising oxygen and methane reed the skies in a gentle, protective haze, fragile life seizes the moment. Filamentous mats ripple with new pigments, harnessing sunlight in ever more inventive ways. Tiny droplets of liquid water, buffered by that shield, nurture shimmering blooms of algae and cyanobacteria. In sheltered tidal pools and vent-fed lagoons, simple protocells branch into branching lineages, some evolving primitive motion, others forging rudimentary communication through chemical signals. Over untold generations, these nascent ecosystems ripple outward, spawning a mosaic of forms adapted to every niche. Under this dawn veil of filtered light, life's grand tapestry begins to bloom in endless diversity.
In the still, sunlit shallows of early Earth's oceans, photosynthetic pioneers, tiny cyanobacteria, begin to capture the energy of sunlight. With each beam absorbed, they split water molecules and release oxygen, a gas never before seen in the atmosphere. Slowly, their quiet labor transforms the chemistry of the planet, flooding the seas with reactive oxygen and altering the balance of life-supporting elements. Iron rusts, greenhouse gases decline, and the skies begin to shift. These microscopic architects, invisible to the eye, lay the foundation for complex life, forever reshaping Earth through the quiet power of light.
Over millions of years, the relentless breath of photosynthetic microbes releases more and more oxygen into Earth's atmosphere. Slowly, this invisible tide begins to strip away the dense orange-hued haze of methane and other greenhouse gases that once cloaked the planet. As oxygen rises, the thick veil thins, allowing more sunlight to reach the surface and subtly cooling the Earth. Skies once shrouded in murk begin to clear, revealing the first hints of blue. This gradual oxygenation not only transforms the atmosphere, it marks a turning point, unlocking the path to more complex life and a more visible, vibrant world.
As Earth's climate spirals into a deep freeze, glaciers creep from the poles and icy sheets engulf the oceans, locking the planet in a global winter. Snowball Earth. Sunlight reflects off vast white expanses, plunging temperatures even lower, and the seas freeze nearly to the equator. Yet life endures. Beneath the ice, near hydrothermal vents, and in sheltered brine pockets, resilient microbes cling to survival, drawing energy from the deep. These hidden refuges become sanctuaries in a frozen world, preserving life through one of Earth's most extreme chapters. Proof that even in the coldest silence, life finds a way to endure. Deep beneath the frozen surface of Snowball Earth, where sunlight cannot reach, hydrothermal vents erupt from the seafloor. Cracks in the crust releasing superheated, mineral-rich water. Around these fiery plumes, warmth and chemistry combine to create oases of life in an otherwise hostile world. Here, hardy microorganisms thrive, drawing energy not from light, but from the earth itself, using sulfur and methane in place of sunlight. Towering mineral chimneys teem with microbial colonies, clinging to the heat and nutrients rising from below. In this eternal darkness, far from the frozen wastelands above, life not only survives, it flourishes in the planet's hidden heart.
Over eons, tiny genetic tweaks accumulate within microbial genomes, unlocking new metabolic pathways and survival strategies. A single mutation might enable utilization of novel nutrients, while gene duplications grant fresh biochemical tools. As these genetic innovations spread through populations, lineages branch apart, each adapting to unique niches, from sunlit shallows to scalding vent plumes. In this microbial world, diversification accelerates. Metabolic webs grow more intricate, ecological roles multiply, and the tree of life expands its earliest roots. Through the quiet power of mutation and selection, simple cells give rise to a dazzling tapestry of microbial diversity.
In the sunlit shallows and shadowed depths of Earth's early oceans, diverse microbial mats and tiny eukaryotes weave together into interlinked communities. Some cells break down organic matter, releasing nitrogen and phosphorus back into the water, while others harness sunlight to produce fresh biomass. Still others consume byproducts, transforming sulfur and carbon compounds through intricate chemical pathways. Filamentous bacteria form scaffolds that trap nutrients, and planktonic algae drift overhead, exchanging gases with the atmosphere. Through this complex web of producers, consumers, and recyclers, essential elements circulate continuously, sustaining life in every hidden nook of those ancient roiland seas.
Locked within ancient rocks, barely visible to the naked eye, are the faint imprints of Earth's earliest life. Tiny fossils left by microbes that once clung to wet shores and shallow seafloors. These delicate patterns, etched in stone over 3 billion years ago, preserve the shapes of filamentous bacteria and dome-like microbial mats. Layer by layer, sediment buried their remains, turning once living forms into mineral traces. Today, scientists study these subtle marks, microscopic ridges, pits, and textures, as precious clues to life's first appearance. In each weathered slab lies a whisper from a world long vanished, revealing how life began to leave its mark.
As oxygen continues to build in Earth's atmosphere and oceans, it becomes a powerful force of change, reshaping environments that once favored anaerobic life.
for countless microbial communities that thrived in oxygen-free conditions, the rising levels proved toxic. Ecosystems collapse and species vanish in waves of extinction deep beneath the surface. In their place, new oxygen-tolerant microbes emerge, evolving strategies to survive and flourish in this changing world. This global shift, invisible from above, marks one of Earth's earliest mass turnovers, an unseen revolution beneath the seafloor, driven by the breath of tiny organisms that change the planet forever.
In the ever-evolving seas of early Earth, a profound leap unfolds. Simple cells begin to evolve into more complex forms. Internal compartments emerge, membranes fold inwards, and organelles like nuclei and mitochondria take shape. These innovations give rise to eukaryotic cells, capable of greater efficiency, communication, and specialization. With them comes the potential for multicellularity, cooperation, and true biological complexity. These new cell types diversify rapidly, colonizing new environments and forming the foundation of future plants, animals, and fungi. With their arrival, Earth's biosphere transforms from a world of lone survivors into a stage for life's next grand expansion.
Though billions of years have passed, echoes of Earth's earliest life still endure in the planet's hidden corners. In scalding hydrothermal vents, hypersaline pools, and oxygen-starved sediments, ancient microbes cling to existence, living relics of a primal world. These extremophiles, nearly unchanged through time, mirror the resilience of life's first forms, thriving where few others can. Their metabolisms, genes, and behaviors offer rare glimpses into life's beginnings, preserved in the present. In their quiet persistence, these organisms remind us that the story of Earth's origin isn't just written in stone, it lives on, deep beneath our feet and in the most unlikely places.
From the fiery depths of Earth's newborn oceans, where molten rock met turbulent water and lightning lit the skies, the foundation of life was laid. In scalding vents and storm-lashed shores, chemistry turned to biology. Simple molecules assembled, evolved, and began to replicate. Over eons, these humble origins gave rise to thriving microbial worlds, complex cells, and eventually the vast web of life we know today. Every living thing traces its lineage back to this ancient crucible. From ocean's fire to life's first bloom, the journey of our planet and of us truly began here.